Hey friends, we're going to be multiplying matrices here in section 4.3 of Algebra 2. So as it tells us here, one of the things we need to be really careful about when multiplying matrices is, or knowing if we can actually multiply them, is that the inner dimensions need to be the same of the two matrices that we're going to multiply, and the outer dimensions can be different, but the resulting matrix that we're going to get will be that of the outer dimensions, right? So it makes a little bit more sense when you actually see us multiply some matrices. So let's do that so this little tidbit makes sense. So to get started with our example, let's just make up a 2-row by 3-column matrix. So there we go. That's my 2 by 3. And let's come up with a 3 by 4 matrix for B, like that. Okay, so now that we have our numbers in place, and by the way, you can have fractions and decimals inside of a matrix. I'm trying to avoid that right now just so I can make the math a little bit easier for us. Let's talk about how we're going to multiply these guys, okay? So when we multiply a matrix, and I have to do this every time, we go horizontal and vertical. So I'm going to multiply the horizontal row by a vertical column, multiply each number with each number of that row with each number of that column, add them up, and that's going to be the first number here. Okay, so in a way, the row and the column, so first row, first column will give me first row, first column. First row, second column will give me first row, second column. You guys see what I'm talking about? Let me do it again. If I do that, and then this one, I get this number here, right? If I do the same thing, multiply each term element in this row by each element in this column, add up those products, I'm going to put that there, and then if I do it again, I feel so bad. Put that thing there. But I'm just being honest. That's what it is. And then you multiply these guys together, and that product sum situation is going to go right here. Then we do it all over again. We're going to multiply. Let me use maybe a faded out color would be better, right? Right? That makes sense. So if I did this one and this one, well, yeah, this one and this one, I'm going to get this here. If I use this one and this one, I'm going to get this guy here. If I use this row and this column, I'm going to get this one. And then finally, let's go for green. Oh no, I already did green. Let's do orange. If I use this one and this one, I'm going to get this here. I know I just said a whole lot of stuff, but try to follow me with it. I'm actually going to do the work, but I just want you to see where all this stuff is coming from. So in order to get this red box, right, this red box, this first one, I told you I'm going to multiply this row and this column and multiply 1 times 1, and I get 1, but I'm going to add 3 times 2, which is going to give me 6. Then I'm going to add 0 times 3, which is just going to give me 0, right? So when I add 1 plus 6 plus 0, I get 7. And that's how I multiply. You see how much work it takes? I mean, it's not that hard, right? The reality is, it really is just multiplication and adding, and you guys are, you know, awesomely smart kids, and you can do this easily. But again, I'm going to multiply 1, 3, and 0, this time to 0, 4, and 2, times 0, times 4, and times 2. And these guys fall out, and I get 12 here. You guys see it? Because this 0, that's 0. So I'll finish this off just in case you're interested, and then we'll get to some examples. Okay, so this is the resultant matrix that I got. Notice it is a 2 by 4. Okay? All right, so here in this first example, we're just going to determine whether or not Determine whether each matrix product is defined. If so, state the dimensions of the matrix. You remember that little picture I showed you earlier, right? It said these two have to be the same. The inner dimensions have to be the same. And if they're the same, yes, you can multiply them. And if you can multiply them, your resultant matrix will be the outer dimensions 2 by 4. That's the best way to say that, or the best way for me to show that. So this is going to be a 2 by 4 matrix if I were to multiply it. Again, I'm going to check the inner matrix, the inner dimensions rather. The inner dimensions are not the same, and therefore no product can happen here. I cannot have a product of these two matrices. So here we're going to multiply square matrices R and S. We're going to find R and S, and to do that, we know that this is a 2 by 2 and this is a 2 by 2, and we know that since they're the same, these inner dimensions are the same, the outer dimensions tell me that I'm going to get a 2 by 2 as a result. Now that I've confirmed that for myself, what I'd like to do is get started. Remember, I always draw my little arrows. It kind of helps me out. So I'm going to do that one times that one, this one times this one, and that's going to give me the first two entries in my matrix. So 2 times 3, I'm doing this first one in blue, 2 times 3 is 6. -1 times 5 is a -5. So that is 1. I get a 1 for that entry. And now let's do the other one in purple. 2 times -9 is a -18. -1 times 7 is a -7. So -18 minus 7 is going to be a -25. And let me give myself a little bit more space here. -25. All right. And now I need to do the other ones. So this row and this column will give me this value here. And then this row and this column, I'm going to do the same thing I just did, will give me that value there. And I'm going to write the answers in black so you can see them. So 3 times 3 is 9, plus 4 times 5, which is 20. That gives me 29. And then 3 times -9 is a -27, plus 4 times 7, which is 28. -27 plus a +28 is going to leave me with a +1. And so that's my resultant matrix. Let me write this a little bit prettier. Okay, so we should have 1, -25, 29, and 1. I don't remember what I said when I did 6 minus 5, but we know 6 minus 5 is +1. If I said something other than that, my bad. All right, so let's look at this guy. Multiplying matrices with different dimensions. In a 4-team track meet, 5 points were awarded for each first place finish, and 3 points were awarded for each second place finish, and 2 points for each third place finish. Find the total number of points for each school. Which school won the meet? So the first thing we did is rewrite that matrix that represents the scores or the places, the number of people they had in different places, depending on the school. And so the next thing that we're going to do is think about how we can incorporate the 5 points, the 3 points, and the 1 point. So one thing that we could do is perhaps make a matrix like this, 5, 3, and 1. And the reason why I'm thinking about that is because I know that my row has to match my column, right? The number of elements in my row has to match my column, and that's the only thing I need. So having this 4 by 3 matrix and this 3 by 1, I can multiply them. But what would that mean? What would the resultant matrix refer to? So when I look at this and I think about that, I'm contemplating, I know I'm going to get some kind of a matrix. I'm going to get a 4 by 1, right? So I'm going to get 4 individual values, but what would those values mean? Let's think, I'm taking information from Jefferson School. I'm multiplying 8 by 5, 4 times 3, which makes sense, and 5 by 1, because the third place kids only get 1 point for their performance. And then I'm going to add it all up. It looks like each column that I create will be the score for Jefferson High, the score for London High, the score for Springfield, and the score for Madison. And that's just the information I need in order to figure out which school won the meet. So let's get started. 8 times 5 is 40. 4 times 3 is 12. And then 5 times 1 is 5. So 40 plus 12 is 52, plus 5 is 57. Let's look at this next one. We have, let's see, we've got 637, and we're going to multiply it here. 6 times 5 is 30, 3 times 3 is 9, 7 times 1 is 7. 30 plus 9 is 39, plus 7 gives me 46. Let's do, what school is this one? Springfield, 5, 7, and 3. 5 times 5 is 25. 7 times 3 is 21. 3 times 1 is 3. 5 times 5 means, so 25 plus 21 is going to give me a 46. 46 plus 3 is going to give us 49. And finally, Madison, we've got 7 times 5, 5 times 3, and 4 times 1. 7 times 5 is 35. 5 times 3 is 15. And 4 times 1 is 4. So 35 plus 15 is going to give me 50. 50 plus 4 is going to give me 54. And that's it. This is the product. And this product also shows us easily who the winner is, which is Jefferson. So here in example 4, we're going to deal with commutativity. So the commutative property like of addition is that A plus B is equal to B plus A, meaning it doesn't matter the order in which I add. I can move stuff around, but I'm going to get the same result. We have the commutative property for multiplication as well. The question is, do we have commutativity here? And so we're going to do that by trying these two products. We're going to see if P times Q, which is written out here, is the same as Q times P. First thing we should check out, I have equal sign here, I don't know why. The first thing we should check out, let me get rid of that. First thing we should check out is whether or not we can multiply these matrices. So can we do a 3 by 2 and a 2 and a 2 by 3? Yes, we can. What would the result be? The question is, what's the result? The result would be a 3 by 3 matrix, right? Because of those n values. And then over here, this 2 by 2, this 2 by 3 and this 3 by 2 can also be multiplied together, right? Because those inner dimensions are the same, but the outer dimensions are going to give me something different. We're going to get a 2 by 2. And clearly, this already tells us that the commutative property for multiplying excuse me, for multiplying matrices does not hold true. But let's multiply them anyway. Again, I start off with my helpful arrows letting me know what to do. 8 times 9 is 72. Negative 7 times 6 is a negative 42, which is going to add up to give me a positive 30. And I'm going to do that straight across. And after multiplying and adding through, I got 30, 17, and 51. I'm going to do the next row. And I'm going to go through all the columns to get my next row, right? I'm going to make this a little bit bigger so I have some more space. All right. And so I'm going to actually move this guy up so I can get even more space. So do that. All right, great. So I'm going to do the same thing. Negative 2 times 9 gives me a negative 18. 4 times 6 gives me a positive 24. 24 plus a negative 18 leaves me with a positive 9. I'm going to continue that process all the way through. And here are the values that I got here. And let me do this last one. 0, 3 times each of these columns. I like the 0 because it's going to knock out all the first values. So this is going to be easy for me to do. 0 times 9 is 0. 3 times 6 is 18. 0 times that is 0. 3 times that is a negative 3. 0 times that is 2, is 0 rather, and 3 times that is a negative 15. So I have this, and I'm going to come over here and do the same thing. I'm going to multiply this row and this column. And here's what we got as our final answer. This last screenshot shows us a couple of properties that do work with matrices. If we were to multiply two matrices and then multiply a third one, making sure we multiply in this order, we would get the same result if we multiplied these two first, but then put the A value first, the A matrix first, and multiply through. Please take a look at this because this will save you some time with the work we do for our assignment. And if you have any questions, please let me know. If not, I look forward to talking to you soon. Take care.